for many years was not even something that you would have heard of in pharmaceuticals. Up until about 2006, when the first publication on water activity was found in USP, and this was USP 1112. This was an informational chapter, not an official method. So its purpose was to introduce this idea of utilizing water activity and some of the things that you could potentially do by having water activity, but not an official method for the measurement of water activity. And really what was outlined and focused in this USP 1112 was that you could utilize water activity to optimize formulations, reduce degradation, but mainly it was for reducing the susceptibility of formulations to microbial contamination, and in addition, providing a tool for reducing the frequency of microbial limits testing. And that was really the biggest part of it, because up to this point, the only way that you could assure the microbial safety of your pharmaceutical product was to do a microbial challenge study. So basically, you're looking at your product, and you determine whether or not there's any kind of microorganisms present, and you have to prove that there are not, and then that would make it safe. But for something like a over-the-counter solid dosage tablet, whose water activity is quite low, there's really no chance for it to support the growth of anything. And so if you can show that through scientific-based information, then there should be justification to reduce that microbial challenge testing that was being done. And so this was really the first attempt to try and make that possible within the pharmaceutical industry, but again, not an official method. So that leads us to the USP 922. So this became official in May of 2021, where it became an actual official method for measuring water activity. And if you break down this method, and if you were to go to purchase a copy of this, what you'll find, the content of it is that there's a section on the theoretical background of water activity, a section on what factors affect it, what types of water activity instruments are there, how do you qualify them, and then a list of applications. So basically the same outline that we're going to follow today is really how USP 922 is structured if you go and take a look at the document itself. So let's start out with what is water activity. So we have another poll question. So please, if you can, please fill out the poll question. But what we're asking here is what is water activity? So it's a multiple choice. So you've got 4 choices you can potentially make. So is it the free water? Is it the bound water? Is it the energy of water? Or is it the amount of water? And this is a really important question because it really gets to the heart of what water activity is and how it's determined and derived. So we'll give you a few more seconds to be able to answer this question before we actually show you what the answer is. Okay, let's take a look at what our results are. So it looks like we got a majority of the folks answered the free water. We had somebody answer the bound water. We had one answer for the amount of water, and then we had 4 people vote for the energy of water. So interesting. So it's not unusual for a free water to be the most common term or definition used for water activity. It is how it's been referred for a long time and still remains a way that people refer to water activity. However, the correct definition for water activity is actually the energy status of the water in the system. Free and bound those terms don't have any scientific definition associated with them. So they can mean a lot of different things depending on the connotation. And so we try to stay away from those terms, free water, in talking about water activity, because it really doesn't describe what water activity is. Water activity is actually derived from the fundamental laws of thermodynamics, something called Gibbs free energy equation, which tells us that uh, if you want to know what the potential energy, the chemical potential energy is of water, then you need to know something about its fugacity, or how readily it can escape into the vapor phase, and that capability is directly proportional to its chemical potential energy. So water molecules in of themselves contain a certain amount of chemical potential energy based upon the interaction that's happening between the two hydrogens and the oxygen. When water goes through interactions with other materials, there's a transfer of that energy, some of that energy, from the water molecule itself into the interactions or the bonds that are happening. And as a consequence, that water molecule's energy has been reduced. And when that energy is reduced, that water molecule then loses its capability to be able to translate into kinetic energy and to escape into the vapor phase. And so if we want to know something about the energy of water, or any material for that matter, what we look at is how readily can that material, in this case water, escape from the product itself into the vapor phase. If there's a high level or number of water molecules whose energy is high enough to escape into the vapor phase, then you're going to exert a higher pressure in the headspace above it. And eventually you'll get to a point where that pressure exerted, or the number of water molecules that are in the vapor state, is going to be what you would get if you had pure water. So really you're talking about a ratio of the energy of water in a product as compared to what the energy would be if you had pure water. And so to determine that, we compare the vapor pressure, or the pressure that is being exerted above a sample at a certain temperature, and we compare that, or divide it by, the vapor pressure that pure water would have under that same temperature. And if those two numbers are the same, then your value is 1. So the water activity of pure water is 1. As that energy is reduced, so there are fewer water molecules that it can escape into the vapor phase, that vapor pressure value drops, which means the water activity goes down. And theoretically, it could continue to go down until there wasn't any vapor pressure from water above a sample. That's not actually attainable on planet Earth, but theoretically, the range does go from 0 to 1, 1 being pure water. So let's take a look at a diagram that kind of helps show us what's going on here. So we've got a sample that we put in a sealed chamber, and that's how we measure water activity. Put it in a sealed chamber and then allow it to come to what we call vapor equilibrium. And again, the number of water molecules that are going to be able to escape up here is being dictated by what kind of interactions water is going in or going through inside these samples. As it interacts with other materials, energy is drawn away out of the water molecule, away from it, into those interactions, and those water molecules essentially can't escape into the vapor phase anymore. That's why you sometimes hear the terms bound, because those water molecules, in a sense, through those chemical interactions, are chemically bound to whatever they're interacting with, and as a consequence are not free to escape into the vapor phase. And so that's where those terms come into play. So they do have meaning if they're used in the right connotation. However, when you just use the terms free water, that could just mean a whole bunch of different things. So that's why we stick with the terms the energy or energy state of water rather than the free water. And so we figure out what is that pressure that's exerted by these water molecules when they get up in the headspace. That's our P value. It's our numerator. And then we divide that by the number of water molecules that are up in the headspace if what we had in that chamber was pure water at the same temperature. So that vapor pressure, and in fact, the vapor pressure of water, or what we call the saturated vapor pressure, that value or that number of water molecules is dictated completely by temperature. Because there, again, if you're pure water, there's nothing else that's interacting with these water molecules. So the only thing that's going to change how many water molecules are in the vapor state is temperature. So if you know the temperature, you automatically know this saturated vapor pressure value. So if we know what that is, again, which we'll know from the temperature, and we measure what this pressure is exerted, or we measure the relative humidity in this chamber, because water activity and a relative humidity are the same thing. It's just called equilibrium relative humidity. But if we figure out what that partial pressure is and divide it by the saturated vapor pressure, then that value gives us water activity. Now, water activity is not the same thing as moisture content. So it's important to understand the difference between these two measurements. Moisture content is a quantitative measure of how much water is in a sample. So you have a product, let's say that if by weight, 10% of that is water. So your moisture content would be 10%. So this is an extensive property that depends on the amount of material, and it requires tracking a weight change in most cases through a loss on drying. Or in the case of pharmaceuticals, often that's determined through what's called a chemical assessment or a Carl Fisher moisture analysis. So that's the amount of water. Water activity is the energy status of water. So while moisture content is a quantitative measure, water activity is a qualitative measure. So it's not based on the amount of material. It's not a quantitative assessment of any kind of amount of water. That's why free water, again, can be confusing. We're not measuring an amount of free water. We're measuring the energy of that water when we talk about water activity. So those are two very different things, moisture content and water activity. Moisture content, which again has traditionally been what is measured for pharmaceuticals through Carl Fisher, simply just tells how much water is there. It doesn't provide any information about what the water is doing and what impacts it may have. For instance, microorganisms, as we'll find out, don't care how much water is present in a product. Moisture content has no correlation to microbial growth whatsoever. The organisms only care what the energy of the water is, and that's water activity. So what are some factors that affect water activity? So remember again that we discussed the fact that when these water molecules, and they're polar, which means they have positive and negative regions, and they like to interact with anything else that's polar. Some of the most the things you might immediately think of are things like salt. Salt dissociates into a positive and a negative ion, and those ions readily interact with water. Water wants to be associated with both positive and negative areas of other molecules. And when those interactions happen, there is a transfer of energy from the water molecule into those interactions, thereby reducing the chemical potential energy of the water molecule. And that particular water molecule that's being associated with these different materials, it could be sugar, could be starch, could be anything that's polar. The water that's interacting with those polar regions has had its energy reduced. It can't escape into the vapor phase and contribute to the vapor pressure. So it causes a reduction in the water activity because that energy of that water has been reduced. So we're talking a macroscopic measure of that energy, not on an individual water molecule basis, but on an overall basis of the product, a combination of all the water molecules. So there's some that are going to have high energy, some that are going to be low. So only the ones that have high energy are going to be able to escape in the vapor phase. As you change that ratio or that number of water molecules through interactions, then there causes a reduction in the vapor pressure and a lowering of the water activity. But also these water molecules that are having these interactions whose energy has been reduced are now no longer going to be accessible to microorganisms because its energy has been reduced, or for chemical reactions to occur. And so that's why water activity has these strong correlations to factors that impact quality and safety of pharmaceutical products. We call these interactions between different molecules matrix effects or surface interactions. Now, there are some other effects called colligative effects and capillary effects that also can reduce the energy of water. They're not as big of factors in a product like pharmaceuticals, but they do play a role. Colligative effects is just simply the fact that if you put a solute in water, then that solute's presence by itself is going to reduce the probability of a water molecule escape into the vapor phase, which will then cause a reduction in water activity. However, because those effects are not having a direct impact on the actual chemical potential energy, it's just impacting the ability of water molecules to escape. They don't play as big a role in the things that we see water activity impacting. Capillary effects also, as you put water into a capillary, it does reduce its energy due to interactions and surface tension. But those capillaries have to be very small to have a very big effect. And in any kind of manufactured product, nature does a good job of creating very small capillaries. Manufacturing processes do not, and so they don't play as big a role in manufactured products. Another thing that impacts water activity and can cause it to change is temperature. And so, as we said in the earlier diagram, to measure the water activities, the vapor pressures, they have to be at the same temperature. And so the temperature has to basically be constant while you're measuring water activity. And that's why it's important to have water activity instrumentation that controls temperature. Because what can happen is, as the conditions in the testing area, laboratory, whatever it may be, if they vary throughout the year, then what you'll see is changes in your water activity values matching those changes in temperature. So if part of the year you're at 20 C and the other year at 26 C, those will give two different water activities. And so by having a water activity instrument that controls temperature to say 25 C, then that prevents the fluctuation that could happen. But it's also important to understand this impact in the case of product safety and quality. So for instance, if you were to make a product to a safe water activity at 25 C, but that product then experiences abuse either at the consumer's home or during transit or during storage, if the water activity goes up, or sorry, if the temperature goes up of that product in the area it's being stored, that will typically result in a higher or an increase in water activity. You can see that shown on this graph. This, of course, is this is for one particular type of product. So that's not going to be exactly like this. This relationship between water activity and temperature is very product specific. It can be modeled, and that's what this Clausius-Clapeyron relationship is. This allows you to be able to model the effect of temperature on any water activity of any particular product, but that model is going to be unique to each type of product. But you can see shown on this, what this is called a moisture absorption isotherm. This is water activity versus moisture content. And what you'll see is at a given moisture level or amount of moisture, as you increase the temperature, so as you go along the x-axis, you'll get an increase in water activity. Even though the moisture level itself is not changing, water activity is going up as the temperature increases. Okay, so how do you measure water activity? Let's do a real quick poll question. This is kind of a fun one just to see if you're familiar with the different ways that you can measure water activity. So on this poll question, what we want you to do is choose which one of these is not a way to measure water activity. So can you measure it with changes in hair length? Can you measure it based upon the depression of a freezing point? Can you measure it by tracking the weight loss at 100 degrees C? Can you measure it using a change in electrical properties of an electrolyte sensor? So which of these, so choose just one, which one of these is not a way to measure water activity? Okay, let's take a look at our poll results and see what how people did. Okay. We had 9 folks choose that changes in hair is not a way to measure water activity. We had 6 choose tracking weight loss is not, and then a couple others. So very good. Uh, Actually, you can measure water activity by looking at the change in the length of hair, but you cannot do it by tracking weight loss. That is how you measure actually moisture content through a loss on drying method, is tracking that weight loss. So that was the one that is not a way to measure water activity, but you can actually do it through the changes in the length of hair. So hair responds naturally to changes in relative humidity. If you put a length of hair in the chamber with your sample and allow it to equilibrate, then based on how that length changes, you could actually track that and use it to measure water activity. In addition, freezing point depression is another way. As water activity goes down, so does the freezing point. So if you're able to measure by how much that freezing point has changed from the standard condition, that should give an indication of what the water activity is. Quite difficult to do freezing point depression because you have to actually detect the point at which ice forms, and that can be very difficult, as well as very tight control of temperature. So not one that's commonly used, nor is the hair hygrometer, because of challenges with repeatability, as well as challenges with volatiles and other things. And it is probably the least expensive way, but just not reliable enough to get used much anymore. Um, so that said, the 3 main ways that water activity is measured is through a capacitance-based system, which uses uh, basically a hygroscopic polymer. This sensor sits in the head space. It's essentially the same sensor that many people use to measure the relative humidity of a room. Because again, remember, what you're actually doing is measuring equilibrium relative humidity in the chamber, in the head space. We don't measure vapor pressure directly in the sample. Every method for measuring water activity depends on measuring the conditions in the head space once vapor equilibrium has been achieved. And that's key, because that's what dictates the test time of water activity, is how long for product it takes to get to vapor equilibrium, which again is very product specific. But this hygroscopic polymer basically, as the polymer itself goes to different water activities, as it equilibrates to whatever the water activity in the chamber is, then there will be a subsequent change in the electrical properties of that hygroscopic material. So it sits between electrodes, and then as the electrical uh, field is interrupted based on the changes in the water activity, you can then plot that and determine the water activity based on those changes. The chilled mirror sensor uses a mirror that is chilled until dew forms. The dew point temperature will tell you the actual partial pressure in the chamber. So that dew point is dictated by the partial pressure. As the partial pressure goes down, so will the dew point temperature. So if you can figure out what that dew point temperature is for the conditions in the chamber and measure the sample's temperature together, those will tell you what that partial pressure is, and you can measure water activity. There's also a laser method that can look at vapor density in the headspace. And then there's the electrolytic resistive sensor. So this sensor has an electrolyte solution in the sensor itself, which changes again to match the water activity of the conditions it's in, or the sample, which is in a sealed chamber, and its electrical properties of that solution will change, that can be then linked to water activity. Now, in terms of the preferred way to measure water activity in these types of products with this electrolytic resistive sensor, because it's very stable, much less susceptible to contamination than other methods, especially the chilled mirror approach, which if that mirror becomes dirty, it will give erroneous readings. So it has to be checked constantly and frequently cleaned. That's not the case with the electrolytic sensor. It can achieve the highest accuracy possible at 0.003. It meets ASTM standards um, for measuring water activity, or ISO methods for measuring water activity. So any of the standard methods that are out there, including USP 922 now, this electrolytic sensor meets those standards as a way to measure water activity. It's relatively insensitive to volatiles because we can use chemical filters to protect it. So anytime that there are volatiles present, we put a filter in to absorb it. For the chilled mirror, if those volatiles actually get to the mirror, they can co-condense on the mirror and actually result in erroneous readings. So uh, it is really the top sensor in terms of the amount of maintenance that has to happen, its ability to measure all types of samples, its accuracy, does not have any hysteresis, which is what plagues the capacitance-based sensors and causes them to not be repeatable. Now, in terms of qualifying water activity meters, it's important to determine whether or not these instruments are doing what they're supposed to. The good news is for water activity is there's a very straightforward way to check these instruments because saturated salts, slurries, so salts that are at saturation point have a very specific water activity. For instance, sodium chloride at saturation, water activity is 0.753 at 25 C. And that'll always be true. So you can actually use that uh, and create a slurry and put it in the instrument and then take a measurement on it. And if it doesn't measure what that water activity is, dictated again by thermodynamics, then you know your instrument's not reading correct. So these are independent standards whose water activity is known independent of taking a measurement. So you can measure accuracy, whether it's correct or not, and know whether or not there needs to be any kind of an adjustment. So it's a very nice, straightforward process for verifying these instruments. You can also use unsaturated salt solutions. So these are still salt solutions, they just aren't at saturation. The concentration's controlled to match the water activity. The other important thing again is temperature. Water activity always has to be reported with a temperature. If it's not reported with a temperature, it's meaningless because it can never be replicated. Because you have to know the temperature at which it was measured in order to replicate it. So you should standardize by running all your tests at the same temperature, and that most effectively is achieved through instrumentation that does control temperature. So look for that as being a feature when you're looking at water activity instruments. And then from using these standards to do these verification measurements, you can determine the accuracy and precision of these instruments. And it's important to understand the difference between those. So accuracy is how well the measured values match the actual value. So it's essentially the difference between what you measured versus what the actual standard value is. So again, keep in mind, saturated slurries, sodium chloride 753, you measure 752, you measure 753, 751. You can then use that information and determine what the accuracy of the instrument is. So that 0.003 accuracy I talked about, that's how it was determined. And if we think about it in terms of a target, if you're hitting the bullseye, that means you're accurate. If your shots are all together, that means you're precise. So precision is, did you get the same thing every time? Regardless of whether it was correct, is it just the same? So you can be accurate and precise, but you can also be precise but not accurate. And you can also be not accurate and not precise. So it is important to have an understanding of the difference between those because sometimes those terms get used interchangeably. And sometimes you might even see repeatability and reproducibility. These have actually different meanings. Repeatability is the variability of readings on a subsample done by a specific person and with a specific instrument. Reproducibility is the variability in readings taken on subsamples that are utilized on different instruments or taken by a different user or on a different day or at a different laboratory. And so precision is actually the combination of the repeatability as well as the reproducibility. And these 10 are standard deviation values that are measured across duplicate readings, again, done on all the same conditions and then done across different conditions. In terms of sample preparation for measuring water activity, the main thing is that you need a representative sample for most types of pharmaceutical products that would be measured. These are solid dosage or capsules, gel caps. Those types of products, you do want to break the surface because otherwise you'll just read the surface. So cutting on something like a gel cap or crushing like the mortar and pestle with tablets, or even maybe grinding, as long as you're consistent, will give you the most effective readings. It increases surface area, plus you aren't reading just the surface, you're actually reading what is in the interior, and that's really important because you want to know what the water activity is in the most uh, um, susceptible area, where it could possibly be high enough to cause problems. And then with the Novacina instruments, it allows you to adjust your stability setting. So you can have it be more stringent or less stringent. The consequence being there's some changes in repeatability and accuracy. But if you want speed, uh, when you do speed, you very seldom get to have accuracy with it. So there's a give and take there. But the Novacina instruments give you the freedom of choosing how you want to do those readings and what setting you want to choose for running your samples. Okay, so we're going to finish up with our application section. Another quick poll question. Um, this is a true or false. Water activity can be used to control microbial growth, prevent caking, avoid moisture migration, and predict packaging requirements. So is that true? Can it do all of those things, or is it false that can't do all those different things? Go ahead and take some time and answer that question, if you will. And as you're answering, we're going to begin our discussion of water activity applications. And again, this is an integral part of USP 922, the publication itself. It spends a lot of time talking about what you can do with water activity and expands on the list of things that you can do from the previous USP 1112. So there are things that are shown to utilize water activity in this USP 922 that didn't necessarily or were not necessarily shown in USP 1112. So not only does it give us specific instructions about how to measure water activity, it also tells you what to do with it. Okay, so it looks like we got a big majority saying that's true, that you can do all those things. And yes, it is true. So good job on that poll question, or that quiz, if you will. So let's talk about what applications there are for water activity. So you can use water activity to optimize ingredients and how you process these products, what type of excipient you're going to use. Water activity prevents moisture exchange or moisture migration. You can use it to, water activity impacts the rate of reactions, some of which may be degradative to the active ingredient in a pharmaceutical. So you can slow and prevent that from happening with water activity. You can optimize your packaging to prevent moisture exchange with the environment, especially when some of these products can be in harsh environments. You can use it to monitor the safety and quality, specifically microbial safety, and then again use it for justification for reduced microbial testing. So let's talk about each one of these in turn. So in terms of water activity, for every type of product, what you're essentially looking for is an ideal water activity for that particular product, and that will be different for every type of product. But that water activity, the reason why it would be ideal is that it maximizes the shelf life and the quality and stability while having or keeping the efficacy of the product, whatever that may be. And so you're fighting keeping it lasting a long time with making sure that it still remains viable. So over drying or drying to a too low of a water activity is not necessarily a good thing. It's the concept of the lower the better is not really true for products when we deal with water activity in any situation. And so it's important to understand, and especially as you set up a drug release program, to identify what is that ideal water activity for this particular product and set that as one of the specifications during manufacturing so that you're always processing to that ideal water activity range. With the understanding that if you over process or go too low of water activity, or you're just losing product because you're over processing, taking water out where water is the cheapest ingredient. But if you under process, you can also cause problems as well, making it perhaps susceptible to degradation from different types of reactions or from microbial growth. And so it's really important to, again, identify what is that ideal water activity, and process till you just until you get to that ideal water activity, and not over process where you're going to lose, in this case, 5% of your product, just by over processing, thinking that you're making the product better by putting it at lower water activities, when in reality the ideal water activity would be at a higher value, and because you're taking into um, uh, you're trying to account for all the things that water activity could potentially impact. Now, in terms of excipient selection, excipient selection can be one of the most important things for any kind of drug formulation. Its purpose is meant to has several purposes, a bulking agent, but it's also meant in a lot of cases to protect the active ingredient. And so the type or the nature of that excipient can be quite important in determining whether or not it will protect the active ingredient. So here we're talking about things like crystalline excipients versus amorphous excipients. And if it's crystalline, where does its deliquescence point? How hygroscopic is it? What are its dissolution properties? Does it go through phase transitions? And all of that's related to water activity. So for a crystalline material, if you're going to use a crystalline excipient, the important thing here is what we call the deliquescence point, and the water activity at which that happens is called the critical water activity. The closer you edge towards that critical water activity, you start to have capillary absorption of water on the surface of the crystalline lattice, and it starts to stick and become sticky. And so what the consequence is that as you move to this critical water activity, those tablets and the excipients in them start to get sticky, and so as a consequence, you get a big mass of tablets because of moving to a non-ideal water activity. Um, a an isotherm, again, here we have our water activity versus moisture content. This is for sucrose, but these isotherms will actually show you exact point where that happens. It's a 90-degree turn when it goes through deliquescence, and the crystalline lattice essentially dissolves and opens up all kinds of binding sites. So if you were wondering, if you have an excipient and you wanted to see whether it was crystalline or amorphous, one way is to run one of these moisture absorption isotherms and observe whether, if these flat isotherms with this sharp turn is indicative of a crystalline material. Another thing that's important is how hygroscopic a material is, because sometimes excipients need to preferentially absorb moisture while not causing big changes in water activity. And so depending on the range at which your product's water activity is expected to be, could have some impact on what would be the best choice to use as an excipient for that particular product. So some types of products, these crystal materials become very hygroscopic after they go through deliquescence, but prior to that, they're very moisture sensitive. In other words, their water activity will change with almost no change in moisture content until they get to that deliquescence point. More amorphous materials will have a higher isotherm, but will have this distinct inflection point that indicates what we call a glass transition. Now, in terms of dissolution of materials, whether or not that pharmaceutical product, excuse me, is going to dissolve in the place where it's supposed to and deliver its active ingredient, is very specific to each type of matrix. Is infected, obviously, by the excipient choice, but it also can be impacted by changes in water activity. If the water activity changes as a result of exposure or handling or whatever the case may be, and causes some of these phase changes to even start to happen or partially happen, will then impact the dissolution properties. So all of the money that's spent on looking at dissolution of these pharmaceutical products could be wasted, because those properties are going to change if you experience a change in water activity of the product. Excuse me. Amorphous excipients. So these are excipients that are traditionally created through spray drying processing, puts them in this amorphous glassy state, which is a metastable condition. And that's one of the reasons why it's a favored form for these excipients. So as long as you're down in this region where that's in the glassy state, then the stability is quite long for these types of products. As I said, they're metastable. They will change eventually, but it takes a long time. But if you increase the water activity, there becomes again a critical water activity where if you move beyond that, it experiences what's called a glass transition. So it changes from this glassy matrix to what we call a rubbery matrix, which makes it much more susceptible to all kinds of things happening. Caking and clumping of excipient powders, that's what induces that clumping, is this glass transition, or changes in dissolution properties, all as a result of moving past this critical water activity. So again, the point is that for these particular products, once you know where that is, then the emphasis is on keeping them in that safe water activity or that ideal water activity range, regardless of what conditions it might encounter. Another important thing controlled by water activity is moisture migration, and this can be very important when making solid dosage forms that have distinct components, like a gel cap or a capsule with a medicinal material inside. If the medicinal material and the capsule are at different water activities, when they're put together, they will exchange moisture until their water activities come to equilibrium, which won't be the midpoint between them. It's dictated by what the material is, what their isotherm is, of what that actual equilibrium water activity will be. But there will be an exchange of moisture, and it will continue until the water activity is the same, regardless of what the moisture levels are of each of those components. They'll change or exchange moisture until their water activities are the same, because water moves from high energy to low energy. And it actually is possible to even model this with certain types of models, and as long as you know what the isotherm is, you can predict what that water activity will be of each of the components without actually having made it. And so it may be that at 683, because of this exchange that's happening with the capsule and the interior, that at that water activity, the active ingredient would become non-viable, and so this particular product would not be possible. You'd have to reformulate and make the water activities of them be closer to each other to try and prevent so much exchange of moisture as a result of very different water activities. As mentioned, the active ingredient, active pharmaceutical ingredient, is the most important part of these pharmaceutical products. It's what's supposed to deliver the effect or the treatment that's coming from these ingredients. So it's typically in very small amounts, but of very, very high value. And so protecting these active ingredients is one of the main purposes of all processing that happens in pharmaceuticals, including excipient selection and how it's manufactured. But in addition, there are reactions that can potentially occur in these different forms that could cause that active ingredient to break down. And the main ones are hydrolysis reactions and enzymatic reactions. Water activity influences the rate of these different types of reactions. So there again will be an ideal water activity where that rate is low enough to allow it to be stable for the amount of time that it needs to. Again, going lower and lower will slow the reactions, although there are some reactions that actually increase, mainly oxidation reactions at very low water activities. But it is possible over a range of water activities to actually model the impact on the rates of reactions due to changes in water activity and temperature. It's called hygrothermal time, and you can find this in the literature. But it's an effective way to be able to account for both temperature and water activity's impact on rates of reactions that might be important for these active pharmaceutical ingredients. In terms of package optimization, when these products are manufactured and now placed in a packaging, what dictates the conditions of that product in that package becomes the properties of the package as well as the storage conditions that it may be exposed to. So if the water activity, say, of these pharmaceutical materials is at 0.30 and it's in an environment where the outside is 70% relative humidity, there's going to be motivation, or would be possible for water molecules to move from this interior at high water activities out to from the high water activity air at 70% and move through the packaging in and encountering this pharmaceutical products, causing the water activity of those to increase, which could then lead to stickiness on the outside as well as degradation of the active ingredient. So having packaging material that prevents that exchange, and this is called, this property is permeability, sometimes called water vapor transmission rates. That becomes very important in protecting it. And so it's important to have packaging material whose permeability for water is low enough to try and prevent this exchange. But in general, as you lower that permeability levels, you also increase the cost of the packaging. Glass being one of the most non-permeable products there is, but very expensive to make and very difficult to ship. So it is possible to account for what permeability or water vapor transmission properties packaging would need in order to protect a product in various storage conditions, so that you can actually assess what that permeability of packaging needs to be in order to protect the product. And so this is the reason why in a lot of cases you'll find, especially in countries where humidity tends to be high for most of the year, you'll see these pharmaceuticals now being put into blister packs. Those are foil lined pouches, individual for each capsule or each pharmaceutical product. And that's again to protect it from moisture. The aluminum coating on that has a very low permeability or a very good rating in terms of moisture exchange. So it provides better protection for these individual tablets in these areas where the outside humidity could be potentially high. And then to finish up, we have the role of water activity with pharmaceutical or with microbial safety. So again, microorganisms will stop growing at certain water activities, and it differs for each type of microorganism. We can categorize them based on based on certain categories. We can identify water activities that are the minimum for the group. For instance, gram-negative all stop at 0.91 water activity. Gram-positive gram-positive bacteria all stop at 0.86. Yeast at 0.88. Mycotoxin production stops at 0.80. Mold's practical limit is 0.7, and then the absolute limit for all growth of microorganisms is 0.6. There are some xerophilic molds and osmophilic yeast that can grow in between here, but they're fairly rare and not typical spoilage organisms. So this becomes now the important thing for determining whether or not a pharmaceutical product would be susceptible to microbial contamination. Now, water activity does not kill microorganisms. Lowering it doesn't kill them. It simply prevents their proliferation or growth to high enough levels to result in an infection, possibly from consuming that pharmaceutical product. So you can see that solid dosage tablets, for instance, down at 0.4, there's just no possibility that they're going to ever support microbial growth. So doing huge amounts of microbial challenge testing on them just doesn't make sense. All you would need to find is if there was a possible external contamination event, but as long as good manufacturing practices are used, that would be highly unlikely. So it's much more effective to be able to show an intrinsic property of these pharmaceutical products, such as water activity, that prevents them from being able to support growth than it is to try and find those microorganisms through challenge testing. And the reason why this works is that these microorganisms are in a very, very simplified form, a membrane that surrounds a sac of solute. And so this internal to this organism will have a certain energy of water. And again, remember, water moves from high energy to low energy. So as long as the environment around this organism has a higher water activity, then water will move in and that organism will be able to utilize it, and it can grow and reproduce. But if it encounters an environment where the water activity is lower, the problem now is that water moves out of the cell, again, moving from high to low, which reduces the turgor pressure of that cell. And without that turgor pressure, it's not able to function properly and go through its metabolic processes. And so it stops reproducing and growing. And it's forced to go into a dormancy state. Now, while it does this, it tries to adapt by lowering its internal water activity. And each one of these organisms has its own capability, unique capability to do this. That's why they each stop growing at different water activities, that being dictated by how effectively they can change their internal water activity. But even after this, it's maybe a situation where they can't get low enough to try and get lower than the environment, in which case they go fully dormant. Some of them form spores, and these spores are quite resilient. They can last for a long time at very low water activities. They've been which has been the result of some recalls and things like flour in the food industry. But there is the potential in powders for these organisms, salmonella being one of the worst, to be able to survive even at very low water activities for extended times. They aren't proliferating, they aren't growing. So if you consume that, you won't have any problems. The problem occurs when that product, that ingredient, is added into other um, products, and now encounters very high water activity, brings those spores along. And once they're in the ideal water activity, they start to grow, reproduce, and cause an infection. Okay, so we've gone through the different ways that you can utilize water activity, what water activity is. Hopefully, you all will remember after this that the water activity is the energy of water, not the free water. It's the energy of water in a system, and that you've got to feel for how you measure it most effectively, and then how to utilize it for making um, uh, a drug release plan that adheres to the most modern or updated recommendations being found in this USP 922. So, with that all in mind, our last poll question is: do you plan to, based on this poll, the information you found here, do you plan to utilize water activity more in the future? So, if you would be so kind as to answer that while you're doing that, just again, a plug for the LabMaster Neo from Novacina. This is the ideal water activity instrument for pharmaceutical industry. Utilizes the resistive electrolytic sensor we described. So low maintenance, high accuracy at 003. Temperature control in this is the best there is available, from 0 to 60 C. You can set the end of test requirements so that you can make sure you've reached vapor equilibrium. There's filters for volatiles. Um, it comes with reusable salt slurries, so you're not buying your standards over and over again. You can reuse those for up to 3 years. The process for verification is automated through RFID recognition. And one things that stands this out even more is it being fully 21 Part 11 compliant. So if you have to deal with audit trails and control of information to make sure that it's not messed with, then this is by far the ideal instrument. And that, because that is often the case with pharmaceutical companies, that's why this is the instrument that we most recommend for the pharmaceutical industry. We got our results, and thankfully we do see a high number of folks that are planning to more effectively or more fully utilize water activity. We certainly encourage that. And if you're in a situation where you need to obtain a water activity instrument, we would certainly encourage you to inquire and look to Novacina for your instrumentation through your local contacts shown here. And with that, that's my presentation.
Thank you very much, Brady, for the presentation and elaborative information about water activity. We are open for some question now. If you have any question, please write it down in the chat on your right panel. Okay, Brady, we have already one question from Lee. Is the test result of water activity related to the relative humidity of the test environment?
Yeah, so it's a good question. As I stated, water activity and relative humidity are essentially the same thing. It's just we use the term equilibrium relative humidity. So it's the relative humidity measured in a container where you've achieved vapor equilibrium. the relative humidity of the room around where you're running the test will not influence what's happening inside of the instrument once you've shut the chamber, and so when that test is started. However, it will influence potentially the water activity of the product itself if it's sitting out. And so that's why it's very important to not allow your samples, when you're preparing them and going to use them for water activity testing, you should limit the amount of time that they're exposed to the environment or room. So even if that means protecting them from the time that you take them to the time you measure water activity, um, and the sample cups that are used to measure water activity come with lids. Those lids are temporary storage, but they work quite well for temporarily storing it between the time you take it and the time you read it. You wouldn't want to store in those cups for long term because they aren't a complete seal. But you do, again, want to limit the amount of time that your sample is exposed to the room, because every amount of time that it is, it's just changing its water activity to match the relative humidity of the room. So if it's high, it's going to go up. If it's low, it's going to go down. So yeah, that's a good point. But once the sample's in the chamber and you've shut it, now because you've isolated and that chamber's sealed, the environment itself, the relative humidity of the environment is not affecting it at that point.
Okay. Thank you, Brady. We have another question, Brady. So, by controlling water activity, can can we reduce bioburden testing, or eventually maybe eliminating it, for particularly for non-sterile products?
Microbial testing, is that the question, is about
Yes,
microbial
yes,
testing?
yeah.
Okay. Yeah, so so yeah, the purpose of this method, USP 922, and its predecessor, USP 1112, is to give that justification. And basically, how these release programs are set up is based on a risk potential of the different things that could potentially happen to the product. On the food side, we call it HACCP, but it's essentially the same thing. You might have heard of something like quality by design, or QBD. That's another way of being able to assure that, or a paradigm to use to try and create this risk-based approach. But as part of all these things, essentially what you're doing is saying that your risk has been reduced for potential microbial contamination because of the intrinsic property of this material being at very low water activities. It's also found in ICH guidelines, um, um, uh, in attempts to try and harmonize across all the different countries. There's been these guidelines put in place where in them they basically say that if you can show from a scientific standpoint why this drug product can't support microbial growth, then that's a justification for reduced microbial testing. And again, the only way to do that is through water activity, and showing that because of its water activity being low, it can't support that growth. So then you can reduce the amount of microbial challenge testing that's being done.
Thanks, Brady. If you have any question, please write it down in the chat panel on your right screen. Brady, another question, because like, which one is better actually, the Novacina equipment to test the water activity or Carl Fisher titrator?
Okay, so yeah, so another good question. Carl Fisher tends to have a fairly high reputation within the pharmaceutical industry as being the most pure way to measure water or measure moisture content, and that may be true. It is meant to be more specific to water than other moisture content approaches, such as loss on drying, where things other than water can volatilize out. But it's still, even in its purer form, all its purpose is to find out how much water is present. It's a concentration of water. And as we've described, that's not what's determining the things that are happening in these products, especially microbial growth. That's being dictated by the energy of water, not the amount. So whether you measure the amount of moisture by Carl Fisher or by loss on drying, all you're getting at is the amount of moisture. That's not what correlates to these stability factors. That's water activity. Water activity is a separate complete measurement from Carl Fisher. It's a measure of the energy status. Carl Fisher does not measure that. So you cannot replace Carl Fisher with water activity, or you cannot replace water activity with Carl Fisher or that they're equivalent. Instead, you can reduce the amount of Carl Fisher because, again, that's purpose is only just a standard of identity, how much moisture is present, rather than trying to utilize Carl Fisher moistures to try and determine stability, which should all be determined through water activity, which the justification is now given through this USP 922.
Okay, thank you, Brady. If there are some like any question, please write it down. We are ready to accept like 2 more questions.
Sure.
Okay, Brady, another question. How to optimize the formulation? You know, sometimes we cannot choose, right? Like again, like sometimes we have to put kind of like hygroscopic materials in the formulation. Like what is a strategy then, you know, like to avoid, you know, like then like increasing water activity when we mix materials in our formulation? You know, do you recommend any excipients, you know, for avoiding the increase of water activity?
Yeah, so again, excipient selection can be quite important. Uh, the consistency of that excipient once it's chosen also becomes important. So if you expect an excipient to come in with certain properties and to be at a certain water activity so that it's remaining stable, then that has to come in consistently every time at that same level. And so water activity can actually become an effective tool for checking excipients as they come in to make sure that they're consistent, to make sure they're the same water activity so that when you put them into the formulation and you put them into the tablet machine or whatever, wherever it's going, that you're going to get that expected performance as well as then the expected stability. So what amount of moisture those different ingredients are bringing with them is important in determining what that final water activity is. And so monitoring them to make sure that they remain consistent is an effective way to make sure that your water activity of your finished product remains consistent as well.
Okay, thank you, Brady. See, there is no other question in the chat as well as in the Q&A panel. Hey, thank you very much. Again, Novasina and the KSH would like to thank you for joining these webinars. And yeah, again, as I said in the beginning, you will get this presentation slide via your registered email. And then we hope to see you again in the other webinars hosted by DKSH and its partners. Thank you, Brady, and then thank you, everyone.
Thank you. Bye,
Thank you everyone for
everyone.
joining, and thank you, Brady, for the great presentation.
Thank you.